So let's start the class. Greetings of the day to everyone who's present. Um, so uh, we'll continue with this doubt class for fundamentals of electrical engineering, which is being taken by Professor Debapriya Das from IIT Kharagpur. And I am Swastik, a TA for this course, and I am a PhD student at IIT Kanpur. Let me share my screen. So last week we discussed first order circuits. We solved some questions. We discussed how the first order circuits behave, how the corresponding differential equations are solved, and what are the various characteristics that are governed that help us govern the first order circuit systems. Now we'll extend it and we'll introduce single phase AC circuits. Before starting, let's quickly see how single phase EMF is generated. So what happens usually is that if you have a stationary magnetic field, and if you let's say move a conductor in that stationary magnetic field, it a certain the due to the magnetic field, certain forces act on it, and due to that an EMF is produced, which is equivalent to the EMF is equivalent to, let's say, if the conductor is moved what you can say normally to the magnetic field, that is, the movement of conductor is orthogonal to the magnetic field, right? So if B is the magnetic field, the what you can say, it's Weber per meter square, right? So B is the density of the magnetic field. L is the, let's say, length of the conductor, and if it's moving with the angular with the velocity of v, the corresponding EMF is BLV. So in a similar way, let's say we have another circuit, another conductor, but instead of moving orthogonally or normally to the magnetic field, it makes an angle theta. This angle, if you can see, this angle theta, right? So what happens? The sorry, not this angle. This is 90 minus theta. This angle. So what happens? The EMF that is produced is equal to the amount is equivalent to BLV sine theta. So similarly, what happens is in a magnetic field, you can keep a current, you can keep a loop, or you can create a loop of a certain conductor. And let's draw that figure first. Let's say this is the direction of magnetic field. And let's say this is how the loop is kept in that magnetic field. What happens is it experiences a force, and on the both edges of that loop, what happens? A magnetic field is produced, right? So in total, this magnetic field is equals to 2BLV sine theta, because it's a loop. It's not just one single conductor. It is connected across two different. So Due to this, what happens, let's say that now what is V? V here is the angular velocity. That is, this conductor is rotating with an angular velocity which is equal to, let's say, which is equivalent to V, right? So what happens is, so we can calculate the amount of this V, which is nothing but, since the radius of this coil will be the half of the breadth of the loop, which is p by 2, right? And it's rotating, let's say, with rps of n. N is revolutions per second, right? And obviously 2 pi, because it's rotating, making a 360-degree angle. So what does it come out to be? It comes out to be pi b n. So if we equate this to our corresponding um, value of EMF, EMF comes out to be 2 pi E L sine theta, right? Now, so the area of the loop is what? The area of loop is, it can simply be, let's say, because its breadth is b and the length is L, it's simply BL, right? So it comes out to be 2 pi BNA sine theta. So that's how this whole due to this magnetic field and the rotation of this movement of this conductor or a loop in a magnetic field produces an EMF, right? And it's sinusoidal in nature. That's we can call it as EM, where this is the maximum value, and sine theta, where theta can obviously be represented by the rotation into V, right? The angular velocity into T, how much it's rotating. So that's how we usually represent angular velocity as omega. That's what we should have started with, but no, we can say V is, let's write it as V as omega, because that's a more concise way of writing the value of EM. So that's how a single phase AC voltage is produced, and the corresponding, what you can say, value is EM sine omega t, right? So now let's further discuss some concepts. Since it's a sine wave, I'm just drawing. It's not drawn to scale, so feel free to, yeah. So this is how our EMF will look like, right? So this, because it's a sine wave, it can be represented like this. Now, what usually, so it's the value we are more interested in is the average value, right? So let's discuss what an average value is first. Average value of a waveform is nothing but the area under that waveform divided by the time period or the base of the waveform, right? Now, since for this circuit, let's do it for a sinusoidal wave. Average value of a sinusoidal EMF. So as you can see, for the full cycle, that is 2 pi, with time period is 2 pi. So for full cycle, the average value would be what? 0, right? Because for 0 to pi, it's positive with the same area, and from pi to 2 pi, it's negative. But since we want to find what the average value of this whole waveform is going to be, we find the average value of the half cycle waveform. Because for full cycle, it doesn't matter. It would be 0, right? So for half cycle waveform, how can we write it? As I told you, divided by the total length of the time period, integrated from the overall half cycle into E dt. E, we can represent it as Em sine omega t dt, which when solved would come out to be, let's do it. So this is Em. Sine omega t is cos omega t by omega, right? From 0 to t by 2. Em t by 2 into omega. So for omega can be written as 2 pi by t, right? So 2 pi by t into t by 2 plus cos 0. Again, this can be written as 2 pi by t because omega is what? 2 pi f. F is 1 upon time period. So this comes out to be cos of pi is what? Minus 1, right? So the average value, is it correct? 2 Em by pi. So that's how we can represent our average value or half cycle average value, because the average value of a sinusoidal waveform is anyways going to be 0 because it's equivalent. The positive cycle, half cycle, and the negative half cycle are equal in nature. So E average is nothing but 0.6366, right? So 6367 times Em. That means that the average value is 63.67% of the maximum value. So this is an important concept while solving single phase AC circuits, because most of the times you will be required to find the average values and one more thing, one more value that you're required to find out is root mean square value. Now, generally, the root mean square value is it's useful because it's required because we it's that value of voltage or current at which the amount of heat produced is similar to that of in a DC circuit. Now, why? What do I mean by this? This is an interesting thing. I'm including heating effect, but it's an altogether different quantity, right? It's a mean of calculating the RM. It's a means of calculating the RMS value. So why am I saying heating effect? It's because it's that value. So in which the heating of a resistor is same as that of the corresponding machine that corresponding that of the heating produced in DC value. Right. That's why when I told you at first for single phase, we always represent VRMS and we always represent to calculate power for a time varying circuit. Like for example, we did last week. It's always VRMS, IRMS, right? So the heating that's producing into the in a DC circuit, the same values are taken in that AC circuit, and it's RMS values. So yeah, so how do we calculate RMS? So RMS is nothing different. It's just we take the square root, we square the waveform, the corresponding equation of the waveform, and we take the root over the whole time period and divide it by the total base. So RMS of E is nothing but 0 to Let's call it t by 2 because still half cycle we are going to take. E square dt 1 over t by 2. So that's how we calculate the RMS value of the circuit. So let's calculate. So E is what we can represent E square as EM square sine square omega t, right? Now, can anyone tell me how can we write sine square omega t in just in terms of cos? We want to remove the square term. So how can we write sine square in terms of cos? Can anyone tell me? No. So it can be represented as sine cos square minus sine square 1 minus 2 sine square. So 1 by 2, 1 minus cos 2 omega t, right? So that means it's EM square by 2, EM square by 2 cos 2 omega t. So we can represent it like this as well. So again, we have to take it for the uh, half interval, right? So let's do it. We'll calculate till pi, and then it's let's keep it as t by 2 only. Yeah. So EM we can keep outside. Sorry. EM by root 2 will come outside, and this would become 1 minus 2 omega t whole to t. So can anyone solve this for me? This integral? And quickly tell me what's the answer. Hmm. Let's do it. It's with EM root 2. This would be t from 0 to t by 2 divided by t by 2. And this is minus cos 2 omega t by 2 omega. Sorry. From 0 to t by 2. 1 t by 2. All good. So what's this value? This would come out to be 1. And what is this? The sine 2 omega t from 0 to t by 2? This is 0, right? So the value, RMS value is nothing but EM by root 2. So that's how we calculate the value of RMS voltage for the EMF. So these are two main interesting, what you can say, um, values that we need or we require to solve the single phase AC circuits. And now let's quickly see some more. So for waveforms, let's factors interest for a waveform. So there are some interesting factors that we calculate for the waveform. So someone can ask, what is form factor? So it's the ratio of the maximum value upon the RMS value. So let's say for our sinusoidal EMF, what is it going to be? The maximum value is EM and the RMS value is EM upon root 2. So that would come out to be just root 2, right? So this is, sorry, it's not, it's crest factor. So let's change, sorry, it's crest factor. Form factor is RMS upon average value. So it's EM by root 2 and 2 EM by pi, right? So it's pi by 2 root 2. Right? So that's how some important factors of interest for a waveform. So we calculate it sometimes. So in order to find out what is the, so we could be given a, let's say just the crest factor, and we are required to find what is the RMS voltage going to be. So we can easily do that by remembering how what is crest factor and what is form factor. So any doubts until this point? So we'll move ahead. One more, so before taking doubts, I need to, yeah, symmetrical and unsymmetrical waveforms. So, so symmetrical waveforms, as I already told you, the positive half and the negative half are, let's say, the area under the positive half is equal to the area under the negative half, right? So that's what that's what we mean by a symmetrical waveform. So or you can say that at half the time period, if we place a mirror, we'll get the same waveform, right? So let's say if we have a sinusoidal waveform, right? So if we place a mirror here, it would reflect the same waveform like this. So this is a symmetrical waveform. That's what we mean by the symmetrical waveforms. And unsymmetrical waveforms are definitely the ones that are not symmetrical, right? So yeah. So any questions until this point? So we'll move ahead. Okay, so there is one more interesting concept and it's called phasors. So what are phasors? Phasors are rotating vectors, right? What are vectors? Vectors are the one that preserve both the magnitude, that depict both the magnitude and the direction of a of any you can say quantity, right? So what do we mean by phasors and why is it of interest to us, right? So first let's clarify what exactly a phasor is. So let's say that there is this sinusoidal waveform, right? We were just discussing. Hmm. So I'm not drawing it to scale. So, okay. So let's say this is our what you can say sinusoidal waveform of any EMF, let's say. So these are the maximum values and they occur at pi by 2 of pi by 2 and pi by 2 respectively. And it's given by EM, right? So in between these, if we draw a circle, right? So if we draw a circle and we, so what exactly does this circle depict? Let's say that at one point our EMF is this, right? So and at one point our EMF is, let's say this. This is like this. Let's say 0, right? So what exactly are we doing? So let's say for the same exact movement, that is, this is theta, which is equals to omega t, at which the waveform is being produced, that is this omega t waveform. So it's making the same exact, uh, what you can say, it's representing the same exact phenomena. So at, let's say, some angle theta, it's making this circle. And then at pi by 2, the value is maximum and it's rotating in the anti-clockwise direction, right? So we can represent the whole quantity. Let's say when it was this, it was, let's say, some theta, and then it was minus 90, and this is how we were representing. So the whole effect of the sinusoidal waveform can be represented on a sphere, on this phasor diagram with the phasor rotating at a particular speed at which the waveform is being produced, right? So this helps us in calculating leading or lagging, to check how a certain quantity is leading or lagging the reference quantity. So that's exactly where we require the usage of phasor. So in Sir's notes, you can find, I would take a very long time if I start discussing how leading and lagging would be would come into picture. But if you can draw a similar waveform which is leading, let's say, this voltage. So, and you'll see that the same effect could be shown over here, that how the circuits are, how the two values are leading or lagging each other. So this is up to you. You can draw the similar circle on this same exact phasor, and you'll find out how the quantities are moving with respect to each other. Right. So let's move on to other concepts that we wanted to discuss. Hmm. So phasors are represented as in two forms. More than two forms, let's say. So one is polar form in, let's say, the magnitude and let's say the angle is being represented like this, where the magnitude is represented in front of the angle component, and there is a rectangular form where we use imaginary numbers to represent our, let's say, j times, sorry, r plus j times x, right? So, and we can also represent it like, since we are talking about the same form, it can be represented at like this, v sine theta. And there's exponential form as well, where you represent it like this. So you can choose whichever form you would like to work on, or which you find useful. It's up to you. So it's represented like this, right? So what more was discussed last week? Yeah. Then there was then the instructor discussed. So I am doing this exercise because I want all of you to be on the same page so that once we solve the sample problems, you are able to participate. So please pay attention, and if you have doubts, please mute yourself and let me know. So let's see the steady state response of circuits. So let's say we have a resistive circuit with a single resistor connected across a single phase voltage. Right. So how would the current look like? The current is nothing but the voltage divided by the resistive value, which can be represented as Im sine omega t, and this Im is nothing but Vm by R. And you can see that a resistive circuit has produced no phase difference between the voltage and the current. It's the same. They are not. There is no phase difference between each other, between both of them. And one more thing, we make use of a quantity called impedance. So impedance is what? It's equal to the voltage divided by the current, which is nothing but Vm sine omega t divided by Im sine omega t, which will come out to be just simply R, or we can say R angle of 0. So this is an important concept because an impedance would show us both. It would give us the exact ratio between the phasor voltage and phasor current, and also it will tell us about the phase angle which is produced between the voltage and the current. So we should remember that an impedance tells us the ratio of phasor voltage and phasor current, and it also tells the angle difference between, it's a phase difference, voltage and current, right? So any doubts until this point, and then I'll move ahead. No doubts? Okay. So the other circuit that we are going to, I regressed a bit. It is a purely resistive circuit because there's no other element. So let's discuss a purely inductive circuit. Also, one more thing. What is the power going to be? What is the instantaneous power? Let's first write instantaneous power. It's nothing but the instantaneous voltage multiplied with the instantaneous current, right? Which comes out to be Vm Im sine square omega t. And the average power is given by what? 0 to dt, right? So can someone tell me what is the average power going to look like? So we just calculated the same thing, right? It was Em sine square t. So it would come out to be Vm Im by 2. So you can solve it and you can let me know. And this is what it will look like. So let's discuss purely inductive circuits. Please go through the lecture material carefully that the instructor has shared, because he has drawn some beautiful waveforms too. And from the waveforms, you'll be better able to understand these mathematical relations. Since there is a paucity of time, so I won't be able to draw all those waveforms. So I would request you to please go through them, and this is just a recap of what he taught so that we can solve the questions together. So let's say this is the what you say inductor. So what is the inductor voltage? We last discussed last time. It's L di by dt, right? Is it correct? And what is VL over here? VL is nothing but Vm sine omega t. So if you do the whole analysis, sine omega t dt by L equals to di, integrate both sides, I will come out to be Vm upon omega L cos omega t minus, right? Is it correct? Yes or no? Nothing. Okay, so this can also be written as Vm upon omega L sine of omega t minus 90 degrees. So do everyone agree with the fact that I can represent minus cos omega t as sine omega t minus 90 degrees? Okay. So, so what is the impedance going to be? So impedance, as I told you, it's nothing but Vm sine omega t, that is the voltage divided by the current, which is Vm upon omega L sine omega t minus 90 degree. So if we solve this, we'll get that it's nothing but omega L at an angle of 90 degrees, right? Is it correct? Is it going to be 90 or minus 90? Can someone tell me? It's going to be 90, right? Hmm. And so the magnitude of the impedance is nothing but omega L, that is the angular velocity with which the waveform is rotating, multiply and the phase difference between the voltage and the current is given by 90 degrees. So that means the current is lagging the voltage by 90 degrees, right? Let's quickly discuss purely capacitive circuits and then we'll move on to questions. So, okay, again, similar circuit, we connected across a single phase voltage source, which is Vm sine omega t. This is a capacitor. So, what is the current I? It's given by C dV by dt, right? And what is V? Vm sine omega t. So, what is its C dV? So, this would come out to be Vm omega C cos omega t, right? Which can be represented as Vm omega C sine omega t. Hmm. So what is the impedance here now? Impedance is 1 upon omega C angle positive 90, right? This is V angle 0 and this is Vm omega C angle 90 degrees. So if we do Vm omega C angle 90 divided by, sorry, Vm angle 0 upon Vm omega C angle 90, it comes out to be 1 upon omega c angle minus 90 degrees, right? So what does this mean? So since the phasor difference comes out to be minus 90, it tells that the current is being, so the current is leading the voltage. So let's, I forgot to discuss a very interesting part. Hmm. So since there is no phasor difference, if let's taking current as a reference, the phasor difference is zero. So what is the phasor? So how can we represent the voltage and current for a purely resistive circuit in on a phasor diagram? Sorry, how can we represent phasor voltages and phasor current on a phasor diagram for a purely capacitive circuit? So taking current as a reference, since there is no phasor difference, we can either just simply represent it. Sorry, if this is I, we can either represent it like this, or we can also represent it like this. Both of them are fine, right? So in a purely inductive circuit, I said current is lagging the voltage by 90 degree. So that means if our current is taken as reference, so the voltage is leading it, right? So the phasor diagram for a purely inductive circuit would look something like this. So the voltage is leading the current, or we can say the current is lagging the voltage by 90 degrees. In the similar fashion, since I said current is leading the voltage, that means if you take current as a reference, so the voltage is lagging 90 degrees. So these are elementary circuits. That means these are the building, or we can say stepping stones of what the basic RL or RC circuits are to look like. So that's why it's important to discuss this first. Now, one more thing, I forgot calculating the power, average power. So can you tell me what is the instantaneous power? It's Vm upon omega L, sine omega t, sine omega t minus 90 degrees, right? Or you can say it's right, square upon omega L sine omega t cos omega t. So this means that we can represent it like 2 sine of 2 omega t. Let's integrate it from so average power is what? So can you tell me what is the average power going to be? So if you solve, since it's a sine to omega t under 0 to under the range of 0 to pi, it's going to be from sorry, yeah, from the range of 0 to pi, it's going to be 0, right? So it's nothing but the average power is going to be 0. That means since the inductor doesn't store energy, for half a cycle, it will uh, store the energy that is being transferred from the voltage source, and in the next cycle, it will try to maintain the same amount of current because the instantaneous current won't change across the inductor, and it will supply the power back to the voltage source. Hence, the average power across this RL combination would be 0. In a similar fashion, if you'll calculate PAV for a capacitive circuit, it's going to be zero again, because it won't store, it won't, it stores power and it delivers. It doesn't dissipate it. So average power is always going to be zero for a purely inductive and a purely capacitive circuit. So let's quickly jump to RL circuit. Hmm. So right. So let's take the let's draw KVL. So what is this going to be? I into R plus LdI by dt is going to be V, right? It's going to be V. Now let's take I as Im sin omega t. Let's take I as a sinusoidal current. So this is going to be IMR sin omega t plus differentiation of sin omega t is cos, and omega would come outside. So it's Im omega L cos omega t, which is equals to V. Let's take Im outside. Sin omega t plus Im. Right? That's how you'll write this equation. And so let's try to convert it into a single equation in terms of cos. So it's we know that since this is R and omega t, right? So this is omega L. So the hypotenuse is going to be R square plus omega L square, right? So dividing both sides by under root of R square plus omega L square. Let's call this angle theta. Right. So what is this omega? So in terms of theta, how can we represent R upon under root of R square plus omega L square? So it's cos theta, right? So this will become cos theta sin omega t, and this will become cos omega t sin theta, right? Which is nothing but sine of omega t plus theta. Hmm. So V comes out to be Im under root of R square plus omega square L square sine of omega t plus theta, right? So now if you see, so we got the value of voltage in terms of current, right? We started from current, taking assuming current as a sinusoidal value, which is Im sin omega t, and we found the voltage across the two, across the combination of this R and across the RL combination. So now, what is Z? V upon I, right? So this would be Im under root of R square plus omega square L square angle theta divided by Im angle 0. So that means it comes out to be R square plus omega square L square angle theta. So that's how the impedance is represented in an RL circuit. It displaces, or it creates a phase difference between voltage and current, and the amount is given by theta. And let's also say what exactly it's going to be. So the value of theta is what? Tan inverse. Since this value is known and this value is known, it's nothing but tan inverse of omega L by R, right? So this is omega L by R. So that means Z is the root of R square plus omega square L square over tan inverse omega L by R. So that's how you represent uh, a phasor, this what you can say, an impedance in an RL circuit. Now let's draw the phasor diagram. This is going to be interesting. So taking current as reference, so this is how the current is. So what is VR? The voltage across resistance. It won't produce any phase difference, right? It would be the same value with which it's not producing any difference. So it would, let's represent it as IR, right? Now across inductor, as I said, the voltage will lead the current value. So this is omega L, right? So the equivalent voltage is given by this, which leads with an angle theta. And the theta value is given by tan inverse omega L by R. So that is exactly how you represent a phasor diagram, this whole circuit in a phasor diagram. So any questions up until this point? So please feel free to ask questions. I mean, no question. Okay, so that's how we represent RL circuit. In a similar fashion, you can see how an RC circuit behave and how an RLC circuit would behave. So those things will solve questions, and we'll see if a similar question comes up. So there's nothing different. You take current as I equals to Im sin omega t and try to find out what's the various values of impedance and voltage across it. So let's solve some sample problems based on this week's assignment so that you are. So the first question. So it's visible, right? So can you so it's given that this current waveform is passed through a 20 ohm resistor, and we are required to find out the average power dissipated in the resistor. So can you tell me how can we solve this question? So what exactly is the power going to be? Power is going to be this, whatever this circuit is, instantaneous value of power I'm calculating. Whatever this waveform equation of this waveform of current is squared multiplied by the value of R, right? So let's see. Let's draw this whole circuitry. This waveform. So please feel free to unmute yourself and tell if you have any doubts. Let's work on the next page. So as you can see, the time period of this this whole this waveform is, it starts from here, right? 0.4 seconds. Uh, 0.4 seconds after the point where the current has reached its maximum value, the waveform starts. So that means this is the whole time period, and this is going to be what, 3.6 plus 0.4, which is 4.0, right? So the whole waveform is between these 2 points, right? And it repeats after each 4 seconds. So on a similar waveform, so we require to find I square, right? Let's so IT square is going to be what? So 16, right? And then it's minus 2, which in square would become 4. So that means it repeats in the different. 16. So I'm doing nothing but squaring the whole waveform so that we get how the waveform would look like. And again 16. Right. So this is how our waveform would look like. So what are we required to find? We're required to find ET, which is nothing but I square T R, right? So the average value of which is going to be 0 to 4, 1 by 4 P of T dt, right? R is constant, which means it will come outside. R is what, 20 ohm, right? 20 by 4. From 0 to 0 0.6, it was 16. From 0 0.6 to 2.6, it became 4. From 2.6 to 3.6, it was 0. We won't take that. And then from 3.6 to 4, it was 16 again. So let's calculate this. This is 16 into 0 0.6 plus 4 into 2 plus 16 into 0 0.4. Let's calculate this whole thing. This comes out to be 120. That means the correct option is D. So any doubts until this point? Okay, let's continue. So in the next question, we are asked to find the average power delivered to an impedance 6 minus J8 ohms by a current of 10 cos 100 pi t plus 100 ampere. So how can we solve this question? Can anyone tell me? So first I need to discuss. Let's see, so we need to discuss the concept of apparent power, reactive power, and real power. Real or average power, both are same things, right? Because it's the only power that does useful work. Okay, so let's say we have a voltage which can be written in the form of V angle theta, and a current which is, let's say, angle 0, I angle 0, right? So the apparent power QP, the apparent power is represented as VI conjugate. Now, why do we take VI conjugate? It's because, let's say we have, let's say, some theta dash. So we need to find the phase angle difference between voltage and current, right? If we just take VI, simply VI, we won't be able to calculate the phase angle difference. So we can either do V star I or VI star, both of which are applicable, but we need to but do remember what reference you're going to take going to uh, when you're going to so it's all about taking reference. So you can take both of them, V star I or VI star, but the thumb rule, generally everyone takes VI star, so that it's the reference value. So what is it going to be? It's V angle theta multiplied by angle I angle minus theta dash, right? So what does this come out to be? VI angle theta minus theta dash. So S can be represented as VI cos of theta minus theta dash. So this was in polar form, that's represented in rectangular form. VI sine of theta minus theta dash. So in this, the real power is nothing but the real part of this whole value, and the imaginary part, which is also called the wattless component. So T is represented in terms of watts, right? So we this imaginary term is the wattless component, which is Q. This is called the reactive power. Now S is nothing but, since it's VI, it's represented as volt ampere or simply VA. Power, again, a real power is a watt component. It represented in terms of watts, while Q is represented as V volt ampere R, which is volt ampere reactive. Right, that's how we represent these three different kinds of power. So again, there's a power triangle, concept of power triangle as well. So let's say you have a current I, which is at an angle theta. So this is going to be I cos theta. This is I sin theta, right? So if we have a voltage, let's say at V angle 0, and we multiply this whole thing, we get VI sin theta and VI cos theta. So a power triangle is nothing but something like this: P, Q, and S. So S can be represented in terms of P square plus Q square. So these are some things that you should remember. So now let's come back to our question again. So what is power? As I said, average power or real power is nothing but V RMS, I RMS. So these V I is nothing but an RMS value, and this is also RMS. So multiplied by cos theta, which is the phase angle difference. Now, as I told you, an impedance represents the phase angle difference between voltage and current, right? So Z is nothing but 6 minus J8, which can be represented as, in polar form, ten at an angle of minus 53.13 degrees, right? So that's how we represent impedance. So that means the phase differences of 53.13 angles, right? So since VRMS is nothing but IRMS into the magnitude of Z, which is IRMS squared into 10 to cos of minus 53.13 degrees. Cos of minus is nothing but cos of the IRMS square is what? So this is maximum value always. At least they haven't told what exactly this value is, but generally, whenever we represent an instantaneous current, the first or the value is generally represented in terms of Vm, right? So this is 10 upon root 2 squared into 10 cos of. So if you calculate it, what is it going to be? So it comes out to be 300 watts. So the answer is A. Right. Let's quickly go to the next question. Let's see this circuit. This is a very good question. So I wanted to discuss it. So it's saying under steady state, what's going to happen to this whole circuit? Now, the answers are incorrect. I'll tell you why. So the answers are wrong. But then again, let's quickly see how the answers are wrong. So let's say, so we need to find the current under steady state, right? But there are two voltages, a DC source and a single phase AC source, right? So let's do superimposition, right? Let's take DC circuit first and then AC circuit. So what would happen? At steady state for a 10 volt DC source, the inductor becomes short circuited, right? And the capacitor becomes open circuited. What is the value of current flowing? I would be 0. Always, right? That's under steady state condition, I would always be 0 because the capacitor becomes open circuited. Now, since the waveform of voltage is changing with respect to with sign, so if we represent, it would be 2, and impedance of an inductance is given by omega L, right? So we represent it as XL, which is omega L. Omega is 2, XL is going to be 4, JXL, J4. And for the current, for the capacitor, it's represented as J upon XC, which is negative, sorry, minus JXC, which is minus J upon 2, always. Right. So the equivalent impedance is what? 2 plus J times 4 minus 1 by 2, which comes out to be 7 by 2, right? 3.5. So we have Z, we have voltage as V10 sine 2t, which is nothing but 10 angle 0. If we see what 2 plus 3.5 iota is in terms of polar forms, it's 4.03 angle 60.25. So that means IT is given as V upon Z. So this is 10 upon 4.03 angle 60.25, which comes out to be 2.48 angle minus 60.3. So none of the so that means sinusoidally it can be represented as 2.48 sine 2t minus 60.3 degrees, right? So that means IT is what? IDC plus IAC, which comes out to be 2.48 sine 2t minus 60.p only. But since none of the answers match R, it was 60.25, right? Why did I write 60.2? 60.25. So none of our answers match, right? So, but the question should have asked what should have the question asked now. Now, if we if we are looking at it, we must know at what value were they. So the question should have asked something related to the average value, but they didn't. They asked steady state. So at steady state, the answer should have been 2.48 sine 2t minus 60.25. So are there any questions up until this point? We'll move ahead then. Feel free to ask for your doubts, and if you're shy in class, you can always comment in the comment section or in the discussion forum. I'll always be happy to help. So let's go to our next question. So here it says that A1, A2, A3 are ideal ammeters, and the value of A1 is 8 ampere, and the value of A2, oh sorry, A3 is 18 ampere. So it's saying what is the value of A2. Now, ammeters always calculate the root mean square value, right? So A3, if it's going to calculate, so since it calculates the root mean square value, it would calculate the sum of square root of, sorry, square root of the sum of squares of the individual A1, A2. That means it would be A1 square plus A2 square, right? So it says A3 is 18 amperes and A1 is 8 amperes, which is 64. So to find A2, it's nothing but 18 square minus 64, right? Which means 82 is under root of 18 square minus 64, which comes out to be 16.12 ampere, right? Always remember that they calculate they give us the root mean square value, hence that's how the individual meter components would look like. Great. So let's move ahead. So these are interesting questions. If you have doubts, please clarify. It could be okay. So does anyone know how we can solve this question? So in this question, we are given parallel branch circuit where there is V1, V2, and V3 voltage sources, each which the values are given above, and they are connected across an inductor of J1 um, J1 impedance and a capacitor of minus J1 impedance, and we are required to find I in the third parallel branch. So how can we solve the circuit? We can easily apply KCL to this point. All your circuit analysis theorems that we discussed are valid to single phase circuits as well. Where they aren't, I'll tell you where they are not applicable once we reach that stage. But whatever you run, KCL, KVL are applicable to um, the single phase or the three phase circuits. So if we say, so it's nothing but V1 upon XL, let's call this as XL and XC, plus V1 upon JXC plus I, right, is equal to 0. This current, this current, this current are all leaving the node. So I is nothing but minus of V1 upon JXL plus V2 upon JXC. So let's solve it. So V1 is 50 angle 0 and the inductor is J1 minus V2 is 50 angle minus 120 degree, and XC is minus J1. Since I've taken minus above, it would be J1 only, right? Since we know uh, J1 can be represented as one angle 90 degree, right? So whenever J or iota, I shouldn't call J, it should be called iota, since I'm trying to distinguish between I for current and I for iota. I'm taking iota as J here. So iota is nothing but when we multiply it to any phasor quantity, it displaces that quantity by 90 degrees, right? So it's represented as one angle 90 degree. So what would happen to this current then if we make use of this fact? So it would look like 50 angle minus 90, since it's in division, minus 50 angle minus 210, right? It's in division. Let's make use of our calculators to find this. So this comes out to be 86.6 angle minus 60 degrees. Now, as you can see, it's minus, so we can say it's 86.6 angle 60 degrees, right? So as you can see, the value here comes out to be positive of 86.6 degrees, but you can 86.6 angle 60 degrees, but you can say none of the answers are matching. That's because what they have calculated is this current, the direction is opposite, but since we are already given the direction of I over here, we have to take that into account as well. So hence it would come out to be the negative of that value, which is 86.6 angle 60 degrees. So always see what the direction is given and then calculate the phasor current, because phasor is a vector quantity, it's a rotating vector, and a direction is an essential component to quantify that value. Okay. Resonance we'll discuss in a bit. We'll finish all the. Hmm. So as you can see in this waveform, this is a current waveform, and we are required to find the value of. We are required to find the average value of the waveform, right? So as you can see, after every 2t intervals, it's repeating itself, right? And what is the average value? Average value is nothing but time period divided by 0 t IT dt. What is this? This is area under the waveform, right? So we can say it's nothing but area under waveform divided by t. Now let's calculate the area under the waveform. So this area is nothing but half into t by 2 into minus ip, right? So this would be minus ip t by 4. Similarly for this also, it's minus ip t by 4. What is this going to be? It's t by 2 into ip, right? So that's it. This part is 0. So let's add all of these areas. We'll get minus ip t by 2 plus ip t by 2 divided by t. Since it's repeating after 2t intervals, we have to divide by 2t, right? So this and this would come, and so average value is nothing but 0. So for this waveform, the average value comes out to be 0. So that's how you calculate the average values for a waveform if your waveform is given directly. Now let's solve this question. Feel free to solve it with me. If you have doubts, please let me know. So what we are given a voltage is applied to a circuit, and the steady state current is given by IT, which both VT and IT consist of a DC component as well as an AC component, and it is found to flow through it, right? So determine the average power delivered to the circuit. We need to find the average power delivered to the circuit. So VT is what? A DC component plus 75 at an angle of 5 by 6 is what? 180 by 6, right? 180 by 6 is 30 degrees. And since it's not on the same, so the transcendental equations are those which consists of sine and cos. So they must be under a same form. That is, since it's a sine term, it should be sine term as well. But if it's cos, it's displaced by an angle of 90 degrees. So we can rewrite this. This would be 25 cos of 2760 minus pi by 4, which can be written as 5 plus. So it's plus 90, right? It would be plus 90. 25 sine 2760. Huh. So minus pi by 4 plus pi by 2 is what? Plus pi by 4, right? So which can be written as 5 plus 25 angle 45. Now power will consist of a DC term plus an AC term. The DC term is nothing but 5 into 75, which is, I should write it like this, 15 into 5, plus the DC term is what? RMS value of current multiplied by RMS value of voltage cosine of the phase angle difference, which is 30 degree minus 45 degree. So this will come out to be 75 plus 905.55, which is nothing but 980.55 watts, right? So that's how we solve it, and it would be nothing but the B answer is correct. So that's how we solve equations when it's given like this. So always remember the base should be same. If it's in sine, voltage is in sine. The current should also be in sine, because if it's in cos, it's displaced by an angle of 90 degrees. Always remember this. Let's see if we have another question. Is on resonance. So since there is time, I want to discuss resonance. So any questions up until this point, please let me know if you have questions. And if you need me to tell you again how a particular question was solved, I'm ready for that as well. So then we'll start resonance, because it's an interesting concept. Any questions? Okay, so since there are no questions, so let's move ahead. Let's discuss resonance. So what is resonance? So as you've seen that, where is it? As you've seen that when we use circuits with inductor and capacitors, or let's say when there is a resistive circuit resistor in connection with a with an inductor, what happens? The current is displaced. So it's sorry. So the current's phase angle is displaced to that of the voltage, right? So there's a phase difference between them. Now, due to this, what happens is that the impedance also faces so the impedance is also at its point of so impedance is also over there, right? And due to the phase difference, the impedance is also magnified, you can say. Had there been a point at which, let's say, in an RLC circuit, let's say, for I think for resonance, I should really okay. So since I discussed RL and RC circuit, let's quickly discuss RLC circuits as well. I was thinking of keeping it for the next class, but so let's discuss RLC circuit in series. Hmm. So how can we write? So there's a resistance, there's a capacitor, and there is an inductor, right? Each connected across a single phase, which is V. This is R, this is C, this is L. Hmm. Now, let's say I have VR. What is VR? VR is simply, let's say some I current is flowing and it's given by IT is given by Im sine omega t, right? So what is VR given by? VR is nothing but IT into R, which is Im R sine omega t. So we have already discussed with the individual circuits. I'm just recapitulating. So what is VL? VL is L di by dt, which comes out to be omega L Im sine omega t plus 90 degrees, right? Sorry, it was minus, so minus 90 degrees. And then VC is nothing but integration of IDT, right? So this comes out to be Im upon omega C sine omega t plus 90 degrees. So that's what we calculated, right? Over here when we did it for individual circuits, that's what came out to be, right? Vm omega C sine. Huh. So just a second. Just give me a second. So I didn't calculate these values, right? I'm so straightforward applying. So let me see. This is correct. So that's how we were writing this whole equation. So, sorry. Yeah, I was correct. It was LD Im sin omega t is nothing but cos omega t. It's not minus cos omega t, and then this will be minus. Right. So that's how this whole circuit was formed, right? So V was nothing but VR plus VL plus VC, which can be written as IMR sin omega t plus omega LIM sin omega t plus 90 degrees plus Im upon omega c sin omega t minus 90 degree. Right. So that's how for a for a circuit, you represent it like this only. But let's say, this is a crude way of doing it, right? You know the value of I, so you calculated the whole VR, VL, and VC, and you got this equation. But what we are interested in is how the voltage is going to look like, right? Sorry, the impedance is going to look like. So let's say impedance is what? VT upon IT. So it was what? R angle of 0, right? Because it was both sine omega t only, I am sine omega t only, plus, so it's omega L at an angle 90 degree, right? Plus 1 upon omega c at an angle of minus 90 degree. And we know, since 1 iota is nothing but 1 angle 90 degree, it's represented in terms of imaginary numbers, right? Sorry, this would be R only, plus J omega L minus 1 upon omega C, or we can say it's nothing but R plus J XL minus 1 upon, XL minus XC. So this is how the impedance for a series RLC circuit would look like, right? Hmm. So now, yes. So now let's draw the phasor diagram for a series RLC circuit. Taking current as a reference, as we did. So what is so how much would the so what is the phase difference between the voltage in this resistor and the current? It's zero, right? Because resistor doesn't produce any um difference, any phasor difference. So we can write VR. Now we know the capacitor will send voltage. The capacitor current would the capacitor voltage would lack the uh, current, right? So the capacitor, so it's lagging the current, which is VC, and the voltage of inductor can be represented as VL, which is nothing but which is IXL, and this is IXC, right? Now we can take this VC and negate it from this value, which is VL minus VC, which is nothing but I of XL minus XC. So the equivalent voltage will be given by this V, right? So that's how you represent the whole what you can say, this whole circuit and a phasor diagram. So that's how it's going to look like. So that means if we take this theta, what is the value of theta? It's nothing but tan inverse of XL minus XC upon R, right? So it's IR upon X, I of XL minus XC divided by IR. So II will get cancelled. It's XL minus XC upon R. So this is how this whole uh, phasor diagram would look like. Now let's talk about resonance. As I've shown above, due to the presence of inductor and capacitor in connection with resistor, the circuit produces a phase. The circuit has a phase difference between the individual current and between the current and the voltage of the circuit, right? What if at a certain you can say frequency, or at a certain value of individual LC, the impedance of the circuit would become purely resistive. That means that the effective value of XL minus XC is zero. That condition is called as resonance condition, right? Under a resonance condition, at a particular resonance or natural frequency, the um, the sorry, the impedance of the circuit becomes purely resistive, and the phase difference is zero, or the power factor is unity, right? Okay, so let's see for a series RLC circuit as we have drawn above. So what did I say? The impedance would become purely resistive. So that means the imaginary side XL minus XC should be equal to zero, which is omega L minus 1 upon omega C should be equal to zero. That means at some omega naught frequency, which is 1 upon under root LC, this condition may happen. So resonance is that part of, or you can say at that particular frequency at which resonance frequency at which the impedance of the circuit becomes purely resistive. So right. So let's say if our circuit is like this, right? With respect to this is impedance and this is omega, which is the frequency. So how is the impedance of the inductance, the inductor varying with respect to omega? It's varying linearly, right? So as omega increases, the XL increases. So that means omega L, right? Now, but for XC, what would happen? Since it's in negative terms, the X is being negated from the XL, right? And since it's 1 upon omega C, it would be something like this. So if you draw the whole circuit thing, so if you superimpose these two with the resistance as well, the waveform would look something like. So the waveform would look something like this. It would tend to become a bit linear because XC would tend to zero, right? That's how the circuit will look. And the point of minima would be nothing but resistance, right? Because the whole waveforms are being added with resistance. So this point at which the waveform is exactly coinciding with with that of the value of R is nothing but omega naught, and at this point the circuit is resistive. So that's exactly what the whole idea of omega naught is. Now, in this direction, the circuit is majorly capacitive because the capacitive value is very high, and in this the circuit value the No, I'm not audible. Yeah, so connection distorted. So let's say this is the circuit, right? So what would happen? So what we need to find is at what frequency would the circuit be resonating? So again, we'll do nothing but equate the imaginary part equal to 0. So this is 4 omega. This is minus 1 upon j4 omega, and this is minus 1 upon. This is minus j upon omega, and this is minus j upon omega. So it's what? So we can write. So and both are in parallel combination. So 4 minus 1 upon omega is in parallel with minus j upon 1 upon omega, right? The parallel combination would be exactly something like this only, right? So can someone tell me what will be the value of omega at which the whole circuit will be 0? So let's do it together. So the parallel combination is what? J into minus j is what? J squared is minus 1 into minus is plus. So this becomes 4 upon omega minus 1 upon omega square divided by the combination of these, right? So it's, sorry, j4 minus 2 upon omega, right? So since the circuit, so what we need is imaginary part equal to 0. J should be 0. So sorry, j xl minus xc should be equal to 0. So equating numerator to 0, we'll get 4 upon omega is equals to 1 upon omega square, or omega is 1 upon 4. Just a second. 4 omega, right? I forgot omega over here. So this would be 4 is equals to 1 upon omega square, and it's omega square is equal to 1 by 4, which is nothing but, so omega naught is 1 upon 2, which is 0.5 rad per second. So always remember that in order to find the resonant frequency, what should we do? We should equate the imaginary part of the impedance to 0. So that's how we can solve this question. So we discussed, so we started discussing single phase AC circuits. We discussed the so we first discussed how the single phase AC generation takes place. We'll further discuss this phenomena in the further classes where the DC motor and induction motor will come into picture. There you will be better able to appreciate the concepts. So in a crude way, before I could have written how E comes out to be EM sin. So simply writing E equals to EM sin omega t, you must not know why this AC, this sin omega t term was coming into picture. So now you'll be better able to understand and appreciate how this term comes. Then we discussed the average values of some waveforms, which is a value that you will be required to calculate because for these circuits. And then root mean square. So a root mean square is nothing but at that value heating effect, that value of, let's say for a current I current, it's that value at which uh, the AC current will produce the same amount of heat as it would produce in a DC circuit. So that's how IRMS comes into picture, because it's what VIRMS into IRMS, which is IRMS square into R. So right. So that's what. So let's elaborate it on a bit, otherwise you won't understand. So what I said was the heat produced in the AC circuit is equal to the DC circuit, right? So that means PAC is equals to PDC. So what is heating effect? It's I square RMS into R is equals to I square DC into R, right? So I RMS is nothing but IDC. So that means when we have two circuits, we can say that it's the heating effect. That's what RMS values mean. So we found out how to calculate RMS values of certain waveforms. Then we discussed some factors of interest for a waveform, which are test factor and form factor, and then how symmetrical and unsymmetrical waveforms come into picture, about phasors, which are rotating vectors. Then we did steady state response of circuits, which were R, L, and C individually, and then we discussed RL only. And I told you to see for RC yourself. And then we discussed some sample problems based on week 8 lectures, and we also discussed the series RLC circuit, steady state response of series RLC circuit, and we also discussed a bit on resonance. So in the next class, we'll further discuss what resonance is. We'll discuss what parallel resonance means and the quality factor. Um, and we'll also start some theorems which are applicable to single phase AC circuits. So, are there any questions or any doubts for today's lecture? You can let me know. So, since there are no questions, we'll meet again in the next lecture. I hope you have a wonderful rest of the day. Thank you.